the second lecture. We are in multiple linear regression, predictive, and I'm looking here. The document that you have a hard copy of is this document right here, MLR with, this should be with, Jump Pro 13. Okay? So I don't know if this is Jump 13, but let me find out. Help about Jump. Yes. And it seems to be fine. I am meeting all of the IT people. I will invite them to the next event of my family. But I had, and I can't see enough about this one kid. His name is Robert Mayo, who works for IT. He's fantastic. There was a problem with OneNote. Here is OneNote. I would change the view to like 150, right? I would zoom in, and it would automatically unzoom. This was a problem in another class. This is a very important lesson for every one of you. Many people came in the past and they just said, I don't know that, and they give up. This kid, he looked at it and she goes, you gave me a very nice problem. He looked at it very positively. She goes, this is a very nice challenge. He found out there's another product called Snapcom, and that, well, he told me nobody else has reported this problem before in all of Northeastern. So by finding out a solution, to cut a long story, make it short, every single user of this OneNote product at Northeastern is helped out. And then OneNote is a Microsoft product, and there's another product involved, Snapcom. There may be a problem with OneNote or this other product called Snapcom. So that means that this problem may exist worldwide. And so, because he pursued it so aggressively, I asked him, who do you work for? He gave me the name of his boss, and I wrote an email to his boss, and I said, Robert knows very well what he's doing. He knows his stuff. Promote him. In your work, when you go to work for somebody, right, do not just rely on doing what is expected of you. Go above and beyond. And when you go above and beyond and you solve problems, you will be recognized. I was teaching at 8 a.m. this morning in 321 Hayden. He showed up. I didn't ask him to show up. He showed up because I told him I had the same problem with 321, 322. He's sending people at midnight to come here, and they did something. You saw this guy who was here, he did something else, blah, blah, blah. And it's all because of this kid. So he did not have to do any of that. But you went above and beyond. This is what you must do to be recognized. Working 9 to 5 and do only what they ask you to do is not going to help you get a promotion. It will not help you make a difference. Okay? So, anyways, very, very important to think along these lines. So, all right. So, and I also have two jump files that I opened up. So now I'm in Jump, and remember last time it would give me Jump would give me a problem. They sent people at midnight. I told them fix it, and they did. So I'm using Jump 30. Anyways, so this is we're gonna go through, and hopefully you'll have the time to go and do some other stuff, some great stuff in addition to this document. But I'm going to follow this step by step. You have it in front of you. So, number one, the purpose. What do I want to do? I have this data file, okay, which is called West Roxbury Housing. And so I got the data. So I'm looking at number 2. This is the data. Know what the data means. It's very important. Know what each column means, and so forth. Number 3, explore, clean, pre-process the data. When I do multiple linear regression, okay, I need to have all columns be numerical. There's one column called remodel, and it has none, old, recent. I don't know how many distinct values it has, 3 or 4. Okay. It turns out that I don't have to do anything because JMP will handle things automatically, but when I say explore, clean, pre-process the data, I mean turn this into dummy variables. Okay, so here's this column. How do we? This is actually not here. Okay, I don't have to do it, but let me show you. We have done this before. So you click the column that you want, column or columns that you want to dummify, and then you go to. There's different ways to do it. Analyze, predictive. Not this one. Columns, utilities, make indicator columns. That's what I mean. Okay. Column utilities make indicator columns. All right. And it says append the column name. So you'll see what it does. Let's just say yes. Let me ignore the other one. Okay. So you see how what it did, it created columns none. Let me click here, Control Shift minus to make it a little bit smaller. So how it created columns none, old, and recent, and it prefixed the name of the variable with the name of the column. That's what it meant. Appends the none to the name of the column, right? So I actually don't need this. Okay. How many of these do I need to keep? Out of these 3? 2. Okay. 2. But what I'm going to do, just so that I proceed, I could do this. I could delete the remodel and one of these 3. How do I decide which one to remove from these 3? It depends on your familiarity with the domain. You can actually, turns out you can delete, remove anyone. But so that you have the output that I have here, I am going to Control Z, leave it the way it is, because JMP, Control Z will do what I just did, right? Automatic. Okay. Number 4, reduce the data dimensions. If it's necessary, you can do it. Actually, it turns out that this is something that we can do later on. Determine the data mining task. What we want to do, you see this total value, okay? We want to be able to predict this is the total value of the house, okay? We want to be able to predict the value of the house. So this is my dependent variable, and all the others are the independent variables. So I want to do multiple linear regression. I want to do linear regression. It's called multiple because I have multiple columns, and this is what I want to predict. This is supervised predictive. Okay, the first task, and this is in item number 6, is to partition the data. Okay. So to partition, you see in number 6, I do analyze, predictive, make validation column. Right? Now, I forgot what I used here. I don't know if I used 0.75, 0.25. I forgot, and I don't. Okay. Well, I forgot. I can change this to be 0.60 and 0.40. And use no test data. Okay, I forget what numbers I used. Anyways, I'm going to call this column partition. What do I have in my notes? Well, I'm going to leave it validation because I don't want to to do something different from my nodes, right? But this column name should not be called validation. It's confusing because you have training data, you have validation data, and you have test data. Okay, now, there's different things that you can do. Let's just click formula random. So this will create this new column, and it will assign 75% of the data to the training, 25% to the validation, and 0% for test. Okay. Down here, and you see how it created this validation column. Anything that has a blue triangle is numerical. So actually, if you double click here, if you click, it's a continuous variable. If I double click here, it's a numeric continuous best. If I go here, remodel, double click, it's a character nominal. It could be numerical nominal if it was 0, 1, the column. Okay? And it's a good idea to put comments here. It's a very good idea to put comments. I'm not sure what this lock is. I haven't played with that. Okay. It's always, if you want to find out metadata information for a column in JMP, double click this, and then you have a lot of things, and you can change a lot of things here. Okay, this is metadata information, and you can also check a lot of the other metadata. This is data about the data. Meta means after. Okay. So we did create we partitioned the data, right? And we know what data is in training, what is validation. We can take this data, sort it, and so forth. All right. There's a million different ways of doing things. I don't want to digress too much because it's easy for me to get off the tangent and do something else. So let me just go by this. So on page, on the next page, you see we're looking at this data. In my output, that says all rows 5804. Somehow I have 5802. Maybe I deleted 2 rows by accident. So where is that document? So I'm looking at, right? So this is where I am. Let me see here, minimize this. So this is OneNote, and one of the nice things in OneNote, and it's a very good tool for you to learn to use, is you can, when you are in OneNote, draw, you can annotate things. You know, if you study together with other people, you can annotate things, and it's, you know, you can do that. So you can move any document into OneNote. All right. So we have training, validation, and test data. I chose not to have a test partition. That's okay. So then we choose the technique. So you have this. We choose the technique. So we know we want to use multiple linear regression. By technique, I mean algorithm. Okay. And so. And I'm saying there, we will use JMP and predict the value of a house in West Roxbury, total value, on the basis of all independent variables except tax. So Y is the response, all right, which is the response variable, which is the total value. This is the column we are trying to predict. Number 8, how do we do that in, how do we do multiple linear regression in JMP? So we do analyze, fit model, right? And you have the help. I highly recommend that you read the help. It helps you a lot. That's why it's called help. Fit the model, right? So you're here, and this is the bottom of page, this is number 8. Right? bottom of page, whatever the page is. All right. So now, on the next page, I'm looking at the fit model dialog box. All right. You can make this bigger. So, total value is my y variable. So the minute you put that there, right? The minute you put that there, you get some other things to change, right? I want to select, click on lot square footage, press this shift, and click remodel, and then drag and drop them where it says model effects. These are the independent variables. And then click drag and drop validation into validation here. All right. I did this before, but now we're going to do the serious work with multiple linear regression. Now, click where it says keep dialog open. Right? I don't have it checked, but anyways. And you see up here it says standard list squares, and this has a bunch of other options that I would like to show you at least one of the others. And then it says emphasis. I haven't played with that. We'll take the default. And I click run. Okay. What the heck is this page? I don't have page numbers. All right, but you know where I am. Right? I don't have page numbers. All right. So, I say keep this dialog option open. I will click run, and I get this. Now, you make a different, actually, you should get, there's some default things that happen, but do you all get what I get? All right. We can modify, there's a lot of things that you can do. By the way, when I'm in jump here, under file preferences, I can set up a lot of things, a lot of defaults. And when I says platforms, one of them, let's see, is there multiple? Fit model. There's a place where I can tell it, be aware of it, that I can tell it what I want to see here by default. But there's a lot of other options. So I actually don't need this. So to minimize, if I click this where it says actual by predicted, and all of this, I can just, to save space, just click this, and I don't need them for now. I'm not saying they're not useful, but for now, I don't need them, right? So that we do not have too much on the screen. I want to cover some of these. And the nice thing is that if I make it a bit smaller, you see that dialog box is still open. That means I can close this, go change something, run it again. Okay. Up here, this effect summary, it gives you the independent variables in the order of importance. This log worth, don't worry about this round, but just worry about the length of this bar. This means that the square footage of the house is the most important predictor, and this rooms is the least important for some reason. Okay. The other item here of importance is the p-value. You see how the most important item, square footage of the lot, has the highest, the biggest, the longest bar, and it has the smallest p-value. The smaller than the p-value is, this is very important. And this is p-value, how p-value works everywhere. Okay? Now remember, whenever you do any kind of a test and you have a p-value, okay, there's an alpha value involved. The problem doesn't say anything about alpha. Alpha is 0.05. There's a lot of statistics behind the scenes here. And you see this p-value, each one of these p-values is compared. If p-value is less than or equal to alpha, behind the scenes, there's a hypothesis testing that takes place. The null hypothesis is that the predictor is not significant. Okay? The alternative hypothesis, this is from stats, the alternative hypothesis is that predictor is significant. Okay. If p-value is less than alpha, if the p-value is less than alpha, we reject the null. They reject the null, which means accept the alternative. Which means that the predictor, right, the predictor is significant. So this is a significant predictor. Same as this, same as this. And you see, you go up until this point, all these predictors are significant. Oop. This one is the first one, but this is very close to 0.05. So basically, these predictors, independent variables, right? Same thing. Predictor, independent variable, same thing. Predictor or independent variable, okay, all of them, or they're all like that, but these are not significant because the alpha, the p-value is greater than the alpha. So what happens is something, if the p-value is very close to alpha, right? Well, then experience kicks in. Should I use it? Should I not use it? All right? So this is, you see, this hypothesis testing behind the scenes. I do not want you to blindly say, oh, this is that, this is that. I want you to understand why a little bit. Okay? I want you to be able to explain this. Now, it turns out that here, I'm not going to do it, but you can click, you can highlight one of these. You can highlight one of these, and then you can remove it. All right? You can add additional ones. You can go and edit. Go back here to edit. All right? Did I exit? Okay, let me, I think all right. So, I don't know what this FDR is. Okay, I want to cover certain things, not everything. I want to cover the important things, not that the others are not important. You see this summary of it right here? Here you have, and we talked about RSQL last time, right? Let me grab a bunch of things here. Let me this, that. Residuals are very important. I don't have the time, but they're very important. There's a lot of things that are very important, but I want to give you because there's a million things here. We cannot cover everything. All right. This is R squared. This is R squared. We want, and this is subjective, we want R squared to be at least 0.70. Where does that 0.70 come from? This is subjectively chosen, right? So if R squared is greater than 0.70, right? In this case, R squared is 81.15. Let's say here R squared is 0.81. Okay? So what this says, and I want you to know this, 81%, let me click this and type here. So 81% of the variability, which is another word to say variance. Let me make this bigger. 16. Variability or variance is the same thing, right? Variance of y, which is the total value, right, is explained by all the predictors taken together. All right. Now, this 0.81 is greater than the 0.70, and this means that the linear relationship between y, total value, and all the independent variables is strong. All right. We also have an adjusted R squared adjusted. This is a more conservative version of R squared. Okay, that means it has less bias. Okay, and it's better to use R squared adjusted than using R squared. Right? Okay. Producing the output can be done by an 8th grader. Interpreting the output properly is what separates you. The root mean square error, right? Okay, I left from here. Root mean square error the root mean square error is an error, is a very important error metric, is a very important error metric. It's basically, this means, I will show you how it's calculated. This is the, another way to say it is root average squared error. You'll see that, right? So this is root or square root, right? When it says root, it means square root. Root average, so you see average mean same thing, right? Average mean squared error. Right? So that is the same as that. They use RASE a lot. Right? Mean of response, that means the average of the response variable is y. So when it says response, it means y. Y is the response variable. That's the dependent variable or predicted variable, all same thing. Predictor is the same as independent variable. There are other names which I can't remember right now. Okay. All right. The regressor is another. Okay. So this, if you remember, we have the actuals, right? We have the predicted, and then we have the error. So if you have actual is the same as yi, this is the same as yi hat, and this is the epsilon I. Right? I can make right, an epsilon here. But easily yi hat. The hat is above. Okay. So let me just put some fake numbers here, and you will see. So if I have 10 and 12, this will be 10 minus 12, or negative 2. If I have 11 and 9, the error is 11 minus 9, or 2. If I have another 10, and this is 13, then this is 3. Okay. So if I find e of I squared, right, then this will be 4, this will be 4, this will be 9. Okay. So if I keep doing this, okay, if I keep doing this, and then total things, right, total things, the number that I get here is sum of squared errors, and that will be, because each one of these is a squared error, that will be 17, right? So sum of squared errors, so SSE, sum of squared errors, 17. You see this root mean square error? So then you find so SSE is sum of squared errors. Right. Then I find the average squared error, average squared error, average sum of squared errors, right? So you have SSE, divide that by 3, right? So 17 over 3, 5.6, something like that. 5.6. So this average square error or mean square error, same thing, right? Mean square error, average squared error. Root mean square error or root average squared error is the square root of this MSE or ASE, right? So that is the square root of 5.6, whatever that is. You see how it's derived? Okay, all right. You will see where these actuals and this predicted show up. I showed you the calculation very easy. So that's a very good and very unbiased error metric. Okay, now this is the analysis of variance, the next one. Right here. This helps us answer, I don't have space here. So this analysis of variance, let's open up another one. Right here. There is another, right here, another hypothesis testing behind the scenes, right? Hypothesis testing, ST for hypothesis testing. Should be uppercase. Let's make this bigger, 16, right? There you go. So, the null hypothesis is that the multiple linear regression model is not significant. And the alternative hypothesis is that the multiple linear regression model is significant. All right? I'm showing you how we use the output. This is very good stuff, right? If I take this right here is a p-value. Remember, anytime you do hypothesis testing, right, you must have an alpha. If alpha is not given, you take it to be 0.05. That's sort of the standard. So this guy right here is the p-value. The p-value. The p-value, when it says less than 0.0001, right? Let's call it 0.00001, right? That means it's basically 0. So I take this p-value and you say because the p-value equals to 0.000, I mean, this is less than, so practically the p-value is 0 here, right? So the p-value is 0, and that is less than or equal to the alpha of 0.5, right? This means we reject the null. We reject the null. And this means also we accept the alternative, right? When you do data mining, you are doing statistics. The trick, and this is what will make you very valuable, understanding and explaining the data. And I'm not going to technical detail. I'm not showing you formulas. Okay? So you accept the alternative, which further means that the MLR model is significant. MLR model is significant, right? So, right here, okay, what is my MLR model? You see this guy right here? Right. the MLR model is this: y hat equals y hat equals. I'm going to take these numbers right here. These estimates, right? I'm going to use this, and I'll talk about this. This is y hat. Y hat means it comes from the sample, equals to negative 6.23 plus 0.00829 times the lot square footage plus 0.035 times the year built. You see what I'm doing? Plus 0.03 times the gross area, and so forth. These, right? You take these numbers from here, okay, and you create. This is the. So you just keep going like that. This is your multiple linear regression. This is an estimate, right? This is the estimated multiple linear regression equation. Estimated multiple linear regression equation, right? It estimates the model. Right? That's the model that we were working with when we were saying here reject or right? Reject the null. When we say the model is significant, this is the model that we're talking about. What happened to it? Right here. So I can take this, and that's the model. All right. Take it out of here, and so I'm jumping back and forth, I know, but this is, you can put it over here. So basically, right, what? Right here, right? I can cut this part here, that's right. All right, all right? So this is significant. That means statistically this is a good approximation of what is happening. These guys right here, are also p-values. If a p-value here, same thing, if a p-value is less than the alpha of 0.05, right? This means, see, these are these guys right here, except the intercept, these are predictors, independent variables, predictors. So if a predictor has a value, a p-value, less than alpha, this means that the predictor is significant. It means we want to keep it. Predictor is significant. Okay? So you see here, the intercept is not a predictor anyways. You see here these guys shown in black, 1, 2, 3. These were also the same things, the same predictors that when I was looking at my effects that had the lowest, this guy's at the end. You see this p-value? It's not a coincidence that you have the same p-values here. You have 0.05571, 0.05557, okay, 0.20 and 0.23. They show up in different places. So you see, it tells you which ones, the ones that have a p-value greater than alpha, you can remove them. You don't have to, but you can remove them. They tell you, right, the output tells you this, that the variables that are that you can remove are the year built, rooms and bedrooms. Now you can say, when you try to find the total value of a house, these items are important. What logical explanation, how can you explain this? You see, the square footage is a significant variable. It knows that the bigger the square footage, the more rooms and the more bedrooms it's implied that you're going to have. In fact, we can take a look at the correlation between this, the square footage and rooms, and the square footage and bedrooms. I bet you that that is high. And remember, when you have two variables that are highly correlated, you remove one. So when you have square footage and bedrooms, you can remove this. Square footage and rooms, square footage, same thing, remove this. So it knows, because it does the, when this p-value is calculated, it takes into consideration the correlation. Okay, now okay. So we did this. Let's skip this. Go over here. You see this right here? We only had training data and validation data. So right here. R square in the training data should be higher than the R square. Yeah, it should be higher than the R square in the validation. We actually have the opposite here. But this can happen, but usually R square for validation, data will be higher, and many times by a lot, than the R square of training. Because the training data, because the model is biased towards the training data, because the training data was used to create the model. This root mean square error, I showed you how it's calculated. Also, the root mean square error for the training data should be lower. In this case, it's higher than, so the root average squared error for training, for validation, right, should be higher. This is what is expected, and this is what happens the vast majority of time. This. All this is telling us is that you have 4,339 records in training and 1,463. That's the 75% of the data is in the training, right? And 25% is in the validation. If you add this up, this is 2, 7, this is 0, 8, and this is the total number of records. Okay? All right. Now, I want to where am I now? So that this is where I am. Okay? This is where I am. Right here. And the next page, in the next page, right? What I want to do, I want to save, and I want you to see, I'm going to make some choices here, and I want you to see the impact of those changes to the table. Here's the table. Right, here's the table. All right, let's look at the end. So I'm going to go here, and I will go to the red triangle and say save columns, the prediction formula, and look what happens here. Right? So this is going to copy here the predicted values using a formula, and you'll see what the formula is. I also want to save the residuals. That's the error. Remember when I did actual minus forecasted the errors? Okay. So this is on that page, and you see it at the bottom of the page. Okay? Right here. So the next page is right here. So the prediction error. So I want to make sure that I go through this document, so I don't want to digress. So, all right. There's something, let's see. Okay. Now, let me, before I go to the next page for the tabulation, let me go here, and you see where it says prediction formula, right? If I right-click, and again, there's different ways to do it. I can right-click and click where it says formula, or I can double-click here and click where it says formula, and this is my formula. This is the model. Remember that? This is the model right here. And remember when I said the remodel jump will take care of it? If remodel is none, it puts negative 9.94. If remodel is old, it will use negative 5.5, and so forth. All right? So this is the formula. And okay, let's ignore that. So this is the prediction formula. That's what you have here. Now, the item that I was trying to predict is total value. If I click and push the button down, wait like for a second, and then drag it, I can move it right here. I want to actually move it. Click, push it down, and move it right here. Right? Click, push it down, wait a little bit, and then move it. There you go. These are actuals, these are predicted, and that's the error. 663 minus 824 is this. So when I was doing, remember there was a place where I was doing this right here, actuals and predicted and the error, right? Well, you have actuals, predicted, and the error. So I can do the same calculations here that I did with the other ones, and you come up with the RMSE that you see. Okay, so you have the actuals, you have the predicted. Okay. Let me see. Okay. Let me skip the tabulate for a little bit. I'll get back to it because I want to make sure that I get to something that is the key. So I want to go to this page because I want to show you why we're doing all of this. Okay, go to this page. Right? Go to this page. What I want to do, I want to save that formula that's here into a depot. I want to put it on the side somewhere. And the way to do that is I do analyze predictive formula depot. You will go to interviews and you will be surprised that you will know a lot more than anyone in the company. This has happened. There are companies that have this software and they don't know how to use it properly. Right? We want to do data mining. We want to predict. Okay, so you click Analyze Predictive Formula Depot. The Formula Depot dialog box comes up. Okay, so we are on this page, all right? And we want to take the formula from here and save it into the Formula Depot. And then you go to the Formula Depot red triangle, okay, right here. Click, make sure that this column is clicked. So click here, right? And where's my, this guy? Click here and say, take the formula from this column and put it in the depot. Well, what column, what's the name of the column? Because you have other columns with formulas. That's the column I want. Click OK. So, you have the table name, you have the total value, the formula for it, and you have the factors, the predictors. Okay? All right. You have to do this in a nice sequence, right? Okay, and you have this in the handout. So in the handout, we are here. When you're here, the next thing to do is you click where it says column this total value, right? Column this total value, and say show script. And this is my script. All right, you did not do any coding. You do not need to do any coding. Okay, now over here, I have two tables because I opened those two tables. Do you guys have two tables? When I was here, I clicked on this and I clicked on that. Actually, you can go and do it now, right? You can go and click this new data, right? Let's say that we did all of the work that I showed you so far today. You go home, somebody emails you a set of new records without a predicted value for the total house. Okay? I just copied this file into that because I didn't have new data, right? So what I want to do, I want to predict the total value for these new records. So if you click this, you should, and then you're going to jump. When you are here, this will show you all the tables that you have open in jump. So if I go into jump, this is the new data, right? I open that. Now this happens to have a total value. It doesn't care what this is. It ignores that. I do not have a predicted value, and that's what I want to do here. I want to add a new column called predicted. You understand what I'm doing? Okay. So I want to predict. So you got this new table, and these are the only columns that you have. I want to predict the total value. Ignore that this doesn't have to be there. All right? I want to predict the total, right? So in my script, I click new data. I change the table name. That's all I do. The script doesn't change. And then I click run. And look in this new table, you get the predicted values. That is why we did everything that we did. Do you understand what we did? We predicted it. Actually, it doesn't matter if this column does not have to be there at all. All right. So it looks. Let me delete it. Let me see, delete this altogether. Let me delete this again. Delete this again. So I go here. I pick the new data. Right. I run it, and poof. I didn't have a value. These are new records that you got. You had all this information, and you predicted the value. Now, prediction doesn't mean that this is exact, right? But this is the most educated prediction that you can make. Yeah.
So did we use the previous model from the thing
Yeah.
that we did just now?
Exactly. Of course, because that's the model. This is the model right here. This is the multiple linear regression equation, right here. Okay? I mean, so from this point onward, every time we use a new algorithm, we will be doing, this is the kind of a thing that we are doing, that we'll be doing. We will be we'll have the software create a model, and then, this is the model. And then, apply this model to new data. Apply this model to new data. And this is, so I showed you multiple linear regression before a little bit, and I told you we're going to go into more detail. We have seen a lot of detail. Okay, now, are there any questions? Right? This is good stuff. Right? If you use a different software, the approach will be slightly different. You click different options, but eventually you will do something very similar. Now, I will close things that I don't need. You can save these tables, by the way. All right? Let me close them. Save, say no. I'm going to close this. Say no. I'm going to close this. Not saving. Because we have too many things open. Over here. I don't want to save it. Go back. Okay. And I'm preparing another document to give you, and that's why I spent a tremendous amount of time to do this, because I was doing it with a different software. Okay. And this is not, what I'm going to show you is not in the document. But basically, this is what I did, right? This was the document initially, right? I created the validation column. No. Analyze predictive. There are many ways to do the same thing, the same way as like in Windows, right? There's many ways to do the same thing. I click that, it created this, then I went and I did fit model to do multiple linear regression. Total value is here, validation is here. I don't pick tax, but I pick all the other columns to be my predictors. And remember, I clicked run. Okay. You see this, by default, includes all of the predictors. Do I need all the predictors? This gives you a good guidance which ones to eliminate, not to use. There are many ways to do that. Okay. Now, instead of standard list squares, by the way, I gave you a whole manual here that covers everything, right? This guy right here has 576 pages. I'm not asking you to read this, but if you want to reference something, you can go there, right? It has detail of everything that we're doing and a lot more. Everything, so you have the documentation. Okay, now you see here, if I click stepwise, see how the other option disappeared? And then I click run. Yep, okay. This dialog box comes up. And I don't want to have too many things open so that not to confuse you. Now, there are many ways to remove insignificant predictors. I'm going slowly, okay? One of them is, well, if you want to look at all possible combinations, because you can have a model with one predictor, or two, or three, or four, or five. So here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You see how it created the two, these two dummy automatically? So you have 12, 13 of these. Okay. If I click here and I say all possible models, this says, give me all possible models. Well, how many terms? When it says terms, how many independent variables do you want to use? You can specify that. Let's just take the defaults, 8, and the number of best models use 56, and then click OK. Look here. It identified all the different models that you can have. This is too much. That ones that are so if you want models that have if you want to look at all the models that have only one predictor, right? You can have a model that has living area only. Use only the living area to decide the price of a house. And then this, out of all of these, the best one is see this one, it has the highest R square, it has the lowest RMSE. This AIC and BIC are two measures, I forget, this stands for Akaiki something something. You want models that have high R square and low RMSE and low AIC and BIC. And out of all of these, if I take all the models with one predictor, you see this is highlighted, the living area, right? The living area is the best predictor. It has the highest of all the R squares. It has the lowest of all the RMSEs, and it has the lowest AIC and BIC. So if you wanted to just use one, you can just click on this one, for example. Out the same thing, of all the two predictor combinations, that's the best one, right? So you can go, this has a lot. This gets to be too much. You can pick any one of these models. Now, okay. If I want to clear this up, to clear the history, if I click this and say clear history, click this, click clear history, all right, no. Okay, the history, I guess, is something, all right. Oh, it was down here, step history. Okay, now, another way, you have all kinds of buttons here. I'm going to show you forward and backward. Forward, there's a stopping rule, there's a direction, and there's rules. The forward means this. We start with no predictors at all. And in each subsequent step, we will add the next significant predictor. Right? So you look at all of this, and you see which one has the lowest p-value, then that's, if there are many, if there's a tie, it picks one. You see this forward, I do not have any, it checks the intercept is not a predictor. If I have forward, right, and I now click go, right, so it actually, because initially I had picked, so it picked a model, and if you go to the step history, it identified this one that has a R square, and there's a CP and there's a P. CP is called Mallows constant, you can read the book. You want a model where CP is very close to P is the number of predictors. So altogether, it has 14. I think it counts the intercept. If you count all of them together with intercept, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4. Okay? Now, so you see that this model here, the one that it picked, all right, is, you see this R square is 0.8124. It also gives you these values of the one that it picked up here, all right? So it knows that this picked all the variables. Okay, now, what you can do, you see this max validation R square, this, it knows, this tells it when to stop. There's a lot more going on here, but I don't want to cover everything. We don't have the time. Now let me remove all of them. Right? Let me, you see this history? I want to clear it. Clear the history. And I want to change it so the direction is backward. And then click enter all. So this says the following. I am including all of the predictors, and I want you to take out the ones that are least significant. So this is the opposite of what we did before. Forward starts with nothing, and it adds the predictors. Backwards, you have everything, and it takes them out one at a time. If I click go, enter all. Okay, go. So let me exit from here. It may be do to, so I want backward. Yeah, okay, there you go. I didn't pick the right thing. Okay, so it also selected the whole thing, and from this, it actually turned out it picked the same thing. Okay. All right.
Professor,
Yes.
what's the difference between a multivariate analysis to a multiple linear regression analysis?
What's the difference between
A multivariate analysis?
multivariate covers many things. Multiple linear regression is just one of them. Do not even bring multivariate analysis into play right now. We will use it for other things. Where did you see that here?
No, because I was thinking before when we learned CPA, like
Multivariate means you have many variables involved. Like here we have many independent variables, right? Multiple linear regression is one of millions of multivariate models. Multivariable only means that you have many independent variables.
because I was thinking of like principal component analysis, because because it's like you see the contribution of each predictor. So what's the difference between that and this?
Okay. You can do principal component analysis and then do multiple linear regression on the result of multiple linear regression. You can do principal component analysis, and then instead of having x1, x2, x3, you have z1, z2, okay? And then use the output of the principal component analysis and do multiple linear regression on that. Okay? Or you can do like what we're doing here, and in some ways we can remove variables from here. So basically do the task of PCA ourselves here, but differently, right? Anytime you remove variables, you are doing dimension reduction. Principal component analysis is one of many ways to reduce dimensions. We're not doing PCA here, but we can reduce the independent variables, right? Now, what you can do here, in both of these instances, the backward and the forward gave us the same model, but this doesn't happen that frequently. What you can do, if I say remove, and I want to do something, if I say remove all, right, and I clicked go before, but let me clear the history. Okay, see if I do step by step, forward, yeah. If I do step, one step at a time. When I do go, it does all the steps for you, right? Step, you can stop at a certain place, find the best model, it tells you which one, and if you like this one, you can stop right here. And then you say, stop, that's the one that I like. Now, how do you know? See, you can create many models, right? For each one of them, you can keep track of the RMSE and a bunch of other error metrics, and then pick the one that has the smallest. Now, once you decide on the model that you want, right? So if I remove all, have forward, and click go, it gave us this as the best model, right? If I do backward, remove all, enter all, create history. If I click go, again, it gave us this model. It doesn't have to be the same as what we did with backwards. Once you are happy with a model, then you can say run model. And you go here and you get the model from here. You get your y hat equation. Okay, I know I'm doing a lot, but I worry about what I have in this document. I showed you more because there's behind the scenes, I mean, you have different ways to eliminate predictors, right? I want you to be aware of this. Once you decide on a model, okay, then, and here, from this one, you can get y hat equals negative 38. You see, this is similar to what we did. Plus 0.008 times lot square footage and so forth. Once you have that, right, then you can create, where's my table? See, I started brand new. I can save this formula here. I can predict using that formula and then save the formula to the formula depot and then use that to predict new data. What I want you to be, what I hold you responsible for is to know what is in this document. I showed you more, right? You can review the video to see because there's a lot going on. But let me show you. I have an Excel file here. This Excel file. This is with no, that's not the file. I think it's this one. Yeah. Okay. You see, in Excel, you can do multiple linear regression in Excel very easily. This is the data. This is my data. In Excel, if you click data, you should see a data analysis toolpack. If it's not there, you can add this very easily. I think I showed that to you before. Click File Options, Add-ins. The analysis toolpack is under inactive. Then you click Go. Then you click Analysis toolpack. Then you click OK. And now you get Analysis toolpack here. So if you have this data, you bring the data analysis toolpack here. And one of these things is regression. Okay, regression. So this says input the Y range. The Y range, this is another data set, is price. Okay. The input X range is everything else. This has to have all numbers here. So you have this and that. I include the labels, leave that at 95. The output range is just click somewhere where you want the output to appear. Let's ignore these things here. Actually, you can show the residuals. Click OK. Oh, I know what's happening. When you click output range, the cursor goes up there. This drives me crazy. This must be I don't know why they do this. So when you click here, somehow it goes up there. Why does it go up there? It should go over here. And it always bites me. So click and then click OK. And this is the numbers may be different, right? But this is you get your, out of this, you get your Y hat line. This is R squared, blah, 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 the same things. This is the analysis of variance table, and these are the residuals. The actuals are here, the predictor here, and these are, okay? Now, you look at this, okay, and you find the predictor with the highest p-value. So out of all of this, right, if I say equals max of this, the highest is 0.82, which is this one, which means I can remove this.
Is that the p-value for a t-test?
This is the p-value that you can use in the t-test, yes, when you do multiple linear regression. Okay, so you see this guy right here. I'm showing you the backwards, right? Because you have all, right? So I want to remove this. So then, you see this has all the variables initially. I find this one has the highest p-value, and I remove it. So then I take the same data set, but no CC. I use this as Y, and these are used less independent variables, right? You understand? And then I do multiple linear regression again, and then you find the one that has the highest p-value. Remove that. Then, so this is met color. So here you have the data set without the met color, right? So then you do the same thing, you find the next one, the next highest p-value, no automatic, no fuel, no doors, and then you have only independent variables that have p-values less than alpha, okay? Now, you, just because you remove this, you may want to use them, right? But these are variables that do not contribute towards understanding the variance of, they don't contribute much towards understanding the where the price of the property, or in this case, the price of the car, where that these independent variables do not contribute in a significant manner to the price of the car. Yes?
The p-value is based on the assumption using the mean of total value.
The p-value, if the p-value is less than alpha, then it says that this is significant.
Based on the assumption we're using, so the hypothesis is that the mean is the total value.
When you do hypothesis testing with when I had one where I was doing hypothesis testing, when you do hypothesis testing with multiple linear regression, there's a p-value in the analysis of variance table that checks to see if your model is significant. Then, when you look at these p-values, okay, let's take a look at, let's go back and take a look at this one right here. So how is this p-value used? This used with the met color, right? So the analysis would be this, for this one in yellow. The null hypothesis would be that met color is not significant, and the alternative is that the met color is significant, right? You follow me? Okay. So the p-value here is 0.53, because 0.53 is greater than the alpha of 0.05. This means that met color is not significant. We fail to reject the null. Okay? That is exactly how we use these p-values. And when something is not significant, you can remove it from the model. You can remove it. You don't have to. All right? Now, I think we're done. But these are very good questions. And there are other very good questions. For example, one of them is, what is the advantage of using all the predictors? If you use all the predictors, then you can find out a combination of predictors that can help you that you will not be able to see if you remove predictors. Anyways, I know that stuff makes you very happy, and I can see it in your face. This is very good stuff. This is very important, and when you go to work somewhere, it will all come to be useful. That's it for today. Next week we will do KNN. Bring that handout that I gave you that had a one-page description for each algorithm. You'll see a one-page there for multiple linear regression. All right. Next time is KNN. Thank you. Have a great day.
Thank you, Professor.
Yes, sir.